627. Today we will do forced, damped, nonlinear oscillator. This is actually called the Duffing oscillator. We will use harmonic balance. The equation is x double dot plus c x dot plus x plus a x cube equals f sine omega t. Now there are a couple of things for you to note. One is there could have been something here, a coefficient set to 1, and this one set to 1. For the pendulum, I showed you how that is done. The other thing is one frequency is incorporated in the forcing. Now the thing is, if it was a linear system, that means if this term was not there, then we can use superposition, and then we can do the solution for each individual frequency and add them up and things like that, but we can't use superposition here. So this is a limited situation, but still something worth studying. Alright, what's the solution? So we will assume that there is a solution with the same period, and we will use one harmonic only. But notice that there will be, because there is damping, there is going to be a phase difference, and so we will keep a sine and a cosine, right? As you know, suppose it was, let us say, a bar sine of omega t plus phi. That is the same as a sine omega t plus b cos omega t for some a and some b, which can be found in terms of a bar and phi. So these two are equivalent representations, and this is the one that is convenient for us. Okay, so as I have discussed in the previous lecture, what we do is we substitute x equals a sine omega t plus b cos omega t into DODE. Transients are gone, this is just the periodic solution, and then we obtain the residual, and using trigonometric identities, we find coefficient of sine omega t set to 0, and we find coefficient of cos omega t and we set it to 0. Those are two equations, and that is going to tell us A and B in terms of C, little a, f and omega. This is the game we are playing. Alright, let's go to Maple, and I think I need to move this window a little here, and I need to move this one up. So here this is the differential equation. I have moved that f sine omega t to the left side. This is my assumed solution. There it is. This is the approximation. I have substituted x equals this approximation into the differential equation, and this expand makes sure that the derivatives are taken. Here is something that is long over here, but you see it has cosine cube of omega t. When I use combine the previous using trigonometric identities, then what happens is the cosine omega t cube is gone, and what we have is sine 3 omega t, cos 3 omega t should be there, and so on. So these terms are there. Now, because I have kept only these basic frequencies, as you may remember from your study of Fourier series, this being the residual, if I multiply this with sine omega t and integrate over one period, that means from 0 to 2 pi over omega, what I will obtain is some number times the coefficient of sine omega t, because cos omega t times sine omega t will integrate to 0, cos 3 omega t times sine omega t will integrate to 0, and sine 3 omega t times sine omega t will integrate to 0. Similarly, I can multiply by cos omega t and integrate from 0 to 2 pi over omega, and that will be exactly the same as some constant times the coefficient of cos omega t. Since I am setting it equal to 0, the constant does not matter, and this is why I am pulling out just the coefficient of sine omega t, and that happens to be this here, and the coefficient of cos omega t, and that happens to be this here. These are two equations that I need to transfer to my drawing sheet. So let me see how I can do that. If I can do that a bit efficiently, it will be nice. But I doubt if that will happen. If I touch this, that will go away. All right. Minus a omega square minus cb omega, minus a omega square minus cb omega, plus a plus 3/4 little a cube, plus a plus 3/4 little a cube, plus 3/4 little a b square minus f, plus 3/4 little a b square minus f. This has to be 0, and there is another equation which I will write here now, and that is minus b omega square plus ca omega minus b omega square plus ca omega plus b plus 3/4 a square b plus b plus 3/4 little a square b plus 3/4 little a b cube plus 3/4 little a b cube equals 0. All right. Now these are nonlinear equations. In principle we can solve them quite easily, but what I will do is I will show you a way to understand them simply in an easy way. So to understand them, let c equal to 0, f equal to 0, then omega is irrelevant. So this is the unforced undamped case. When I do that, we do that with blue here, I'll get minus a omega square plus a plus 3/4 little a cube plus 3/4 little a b square equals 0. That's 1. And minus b omega square plus b plus 3/4 little a square b plus 3/4 little a b cube equals 0. And now something interesting happens. You see this solution B equals 0 satisfies that equation independent of A. And then this equation gives you minus A omega square plus A plus 3 by 4 little a cube is equal to 0. So B is 0, and since the amplitude is not 0, therefore omega square is equal to 1 plus 3 by 4 little a square. So this is a rather dramatic simplification, and let us consider the implications of this simplification. Okay? All right. Omega square is equal to 1 plus 3/4 of little a, 1 plus 3/4 of little a square. All right. So let's come here. This I will write as amplitude of the solution, but I'm just, B is 0, so A is the amplitude of the solution. This is omega. Let us assume A greater than 0 for the moment, because that is simpler and easier. This is 1, and over here we will get a curve that looks like this. Asymptotically, see, when omega is very big, A is very big, then omega is very big, and omega and A are linear. So this is asymptotically linear, right? But over here it is parabolic, because for small a, this is parabolic, right? So for small a, omega is equal to 1 plus 3 by 8 a square plus small things. So for small a, it is parabolic. Okay? This curve is called the backbone curve, because it looks like a backbone. And what is interesting is that the frequency of the solution, it's a periodic solution, depends on the amplitude. So if you increase the amplitude, you'll get a different frequency. This we have seen in other situations also. But what happens when the damping and the forcing are present? What can we expect, right? So to understand that, we can go back to the linear case. Linear case, let me use blue here. In the linear case, this is what we have. This is the amplitude. What happens is, without forcing or damping, the backbone curve is perfectly straight. Periodic solutions of any amplitude are possible, and the frequency is independent of amplitude. The omega is 1. Then when we put forcing and damping, what happens is we get something like this. And you have studied this in the SDOF video that I sent. If you haven't, please watch that video now. Okay, so this is with forcing and damping. Okay, now what happens here is, if I reduce the damping and keep the forcing the same, this goes up. This is smaller c. Okay, this part of the curve doesn't even change, because damping is not important here. It changes very slightly. Similarly, if I increase the forcing, in that case forcing amplitude, if I increase f, then this increases like that. This is higher F. Okay, this is higher F. We come back here and basically the same thing happens, but because the backbone curve is bent, so we actually have a solution that looks like this. And then if I have higher F, then it looks like this. If I have, this is higher F. If I have this is higher C. Larger amplitude, this part largely unaffected. This is lower C. Okay, how do we get all these solutions? That is from numerical solution of the harmonic balance equations or other methods. All right, so now what do we say, what do we know about these solutions? So let me come back here and plot it again. So here is the amplitude, here is frequency, here is the underlying backbone curve, here is the actual frequency response, and the first thing to notice is that there is a range of frequencies from here to here. In this range of frequencies, in this range of forcing frequencies, there are 1, 2 and 3 solutions. Okay, so if you have not seen it before, this is surprising. Multiple solutions here. Now what I will do is I will draw a dashed line here to tell you without proof at this time that between these turning points, this is actually an unstable solution branch. Okay, how do I know it's unstable? We will see it in different ways later. For now, I will request you to take my word for it. What happens here? How much is this value? That is relatively easy because omega is 0. So if we go back to those equations, you see, if we go back to these equations, and we say omega is 0, that means this is 0, this is 0, this is 0, this is 0. And then once again over here we will be able to say B is equal to 0, so we come back here, that's 0, you see, and this is basically the response of the stiffness to the force. So it is a pseudostatic response, and you have to solve a cubic equation, but when you solve that cubic equation you can find this value. This is the static response. What about here for large omega? When we look at large omega, we come back here again. So I'll have to erase some of these things a bit, or maybe not. Just imagine that the orange erasures are not there, and now I will do blue. Now for large omega, what will happen is this term will remain, and compared to that, this will be small, this will be small, this will be small. This, let us wait a bit and see. This term will remain. This, let us wait and see, and this will be small, this will be small, and this will be small. Okay, and then you can see that if omega square and omega are comparable, then B is very small compared to A. You know, C is not 0 here, and omega is very, very big. In that case, this equation, where this omega is big, it tells you that B is like A by omega. Okay, so then B is like A by omega, then this goes down. So that's 0 also. This is negligible. And so we have F is equal to minus A omega squared, you see, because this term and this term, they are the only things that remain. So F is equal to minus A omega square, or A is equal to minus F by omega square. This is exactly the same as the linear system inertia dominated response. So over here, inertia dominates linear. Okay, now we come here. This is a stable branch and this is a stable branch. What does that imply? What that implies is, let me use red here. What that implies is, let's say I start at a low frequency, so I get this response. There is only one periodic response, I settle there. Then I slowly increase the frequency of forcing. Suppose I do that experiment, then it will slowly follow this curve, because this curve is stable. It will keep following this curve. It will keep following this curve. It will keep following here, 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 here. And then what will happen is suddenly there is no other solution for it. So it will jump down. There will be a transient. So it will jump down and the amplitude may oscillate a bit, but then it will settle here and it will follow like this. Let me do that with a fatter brush so that you are not confused about it. So here it will go like this and then jump down and go like this. Okay, but when I return, then it will come back like this and it will keep on this curve, because this is stable, and then over here it will jump and then it will come like this. This jump up here and the jump down here don't occur at the same place. So this, you are now noting two things. One is the jump, little fatter, noting the jump phenomenon, and you're noting something that some people call hysteresis, because increasing and decreasing give different responses. Okay, there is something that I would like you to notice, however, which is that in some books, some careless authors, they write, or some people also think that this is true, they do something like this. Okay, they do something like this. Some people draw this, and it is not really correct. This is because from here there are actually initial conditions. Some initial conditions will come here. So there are large amplitude initial conditions that settle on the small amplitude solution. Okay, what happens if instead of this is a greater than 0, that nonlinearity is positive, what happens if a is less than 0? Then it bends this way. When it bends this way, then some funny things can happen. What can happen is this can then go like this and actually turn around. It exists over there. This solution can come like this, and strange things can happen, and there are stability issues here to be studied as well. But we are focusing today on this one. For the moment we are focusing on this one, a greater than 0. This one is our main curve of interest. If the nonlinearity is smaller, weaker nonlinearity, in that case the backbone curve, instead of being like this, will be like this, smaller a. Okay, that's one thing. Another thing is, let's work with this. In this curve, if the forcing amplitude is reduced, then it may come like this, and then this range where 3 solutions are present, that range may disappear and you may just have one solution. Okay, so these are some things to note about this system. The last thing to note is that on this part of the curve, provided damping is low and forcing amplitude is a bit high, almost in phase with the forcing. That means A is much bigger than B. In this part of the curve, almost out of phase. That means A is less than 0. Once again, A is much less than B. Okay, there is a point here somewhere where A is 0 and so B is much larger than A. That is the point where the response and the forcing are exactly out of phase. Okay, then in the original equation, if you understand the energetics of the undamped linear oscillator, you will understand this part and this part cancel, and this part and this part exchange. So all the energy from here goes into here. That's the point of strongest. That's the resonance. That's the resonant response. See, if you, for linear systems, if you look at force and response on an oscilloscope, you will get, imagine that you're seeing this on an oscilloscope. So here you are doing forcing, and here you are doing displacement. Oscilloscope. Then at low frequency you will get a curve like this. It retraces its path. At high frequency you will get a curve like this. This is the linear case. I've seen it. Nonlinear also will be something like that, is what we anticipate. These you can compute and see. And exact resonance is where you get something like that. Okay, that's the resonance. So this is my qualitative description of what we find or what is known about this response. What is known about the response is qualitatively correct for this system here. The analysis of that leads to this overwritten system of equations, these two equations here, which are there on the maple sheet also, and the numerical solution of these equations lead to graphical results like this. And then the stability studies that are not included in the analysis today predict this traversal like this along this line with a jump down and then a return along this curve and a jump up over here. Okay, so all of these things we will see later. Enough for this lecture. Thank you.